Welcome to part 5 of my series of presentations about the best methods to alkylate carbon nucleophiles. In this video, I'll show you some strategies for alpha-alkylating carboxylic esters. This is an important reaction for the preparation of carboxylic acid derivatives. In particular, the diastereoselective alkylation of acylated chiral auxiliaries has been thoroughly investigated. Later, I'll show you also an example of enantioselective alkylation by means of a chiral catalyst. Carboxylic esters are usually not nucleophilic enough and must be deprotonated to react with common electrophiles. Normal carboxylic esters have a pKa of around 29, and stoichiometric deprotonation requires strong bases, such as alkali amides or potassium terzbutoxide. Some more acidic esters, such as phenylacetates or imines of glycinates, can sometimes be alkylated with sodium hydroxide as base. Ester enolates are ambident nucleophiles and can be alkylated at carbon or at oxygen. Most soft electrophiles, however, such as alkyl bromides or olefins, will alkylate ester and related enolates mainly at carbon. Two important potential side reactions include the formation of ketenes by alkoxide elimination from the enolate and Claisen condensation. Both reactions may be prevented by lowering the reaction temperature and by keeping the time between deprotonation and addition of the electrophile as short as possible. Direct alkylation of an ester enolate may not always be the best strategy to prepare alpha-alkylated carboxylic acid derivatives. One important alternative is the condensation of esters with aldehydes or ketones, followed by hydrogenation. This strategy is particularly useful when multiple alkylations of a given ester cannot be suppressed. Both condensations and hydrogenations are often easier to perform than alkylations. The electrophiles are less toxic and hydrogenation conditions are mild and compatible with many functional groups. A further alternative is the classical malonate strategy. Malonates are more acidic than normal esters and can be alkylated with the aid of much weaker bases. Malonates can also be easily olefinated by treatment with aldehydes or ketones and then hydrogenated. Saponification and decarboxylation then yields the alpha-alkylated carboxylic acid. Main advantages of the direct alpha-alkylation of esters for the preparation of carboxylic acid derivatives are the ready availability of starting materials and that these reactions are usually fast. Moreover, the products are stable but still reactive enough to serve both as target compounds and as synthetic intermediates. The main disadvantages are the need of strong bases and anhydrous solvents. Often, low reaction temperatures are also required. Then, some esters readily undergo Claisen condensation, especially the esters of acidic alcohols or phenols. Before the discovery of lithium amide bases, there were no generally applicable methods for alkylating esters. Under the conditions of the Claisen condensation, for instance, that is, with sodium ethoxide as base and ethanol as solvent, not even the ethyl ester of phenylacetic acid could be methylated or benzylated. Phenylacetates are much more acidic and easier to deprotonate than ethyl acetate. It was found that the potassium enolate of ethyl phenylacetate can be prepared from metallic potassium in diethyl ether. In this solvent, however, ethylation with ethyl bromide only gave 34% of C-alkylated phenylacetate. Attempts to alkylate esters with alkali amides in liquid ammonia weren't very successful either, not even after a solvent change before addition of the electrophile. Conversion of ethyl esters into amides was similarly fast as deprotonation and led to large amounts of amides. Even terzbutyl esters, which are quite resistant to nucleophilic attack, were converted to amides to a large extent. The more acidic phenylacetates, however, can in fact be deprotonated with sodium amide in liquid ammonia. Once the sodium enolate is formed, no nucleophilic displacement of ethoxide will occur, unless a ketene is formed. In this example, this did not happen, and the alkylated phenylacetate was obtained in good yield. In this newer example, a terz-butyl ester was alpha-methylated in high yield by treatment with sodium hydride and methyl iodide in DMF as solvent and at room temperature. Despite the excess of base and electrophile, no alpha-methylation of the lactam occurred, what may be due to steric crowding. By the way, mixtures of sodium hydride and DMF are similarly explosive as mixtures of strong bases with DMSO and should not be used. Occasionally, DMF will also formylate strong nucleophiles. A better solvent would be some ether or a tertiary amine. These are more resistant towards strong bases, and polyethers, such as diglyme, may even act as crown ethers and accelerate reactions with sodium salts. In this remarkable example, the goal was to convert the naturally occurring lovastatin into the synthetic simvastatin. For this purpose, a cyclopropylamide of lovastatin was treated with a large excess of lithium amide base and methyl iodide. In only 1 hour at -30 degrees, the ester of lovastatin was completely methylated, the only byproduct being a small amount of N-methylated amide. No etherification of the 2 hydroxyl groups and no eliminations or nucleophilic cleavage of the ester occurred. The cyclopropylamide was chosen because it enabled the saponification of the amide by sodium hydroxide without saponification of the ester. Cyclopropylamines are much less basic than normal aliphatic amines, and their amides therefore much more sensitive toward nucleophiles. In this instance, the amide saponification was further accelerated by intramolecular attack of a hydroxyl group and formation of a 6-membered lactone. This is an example of enantioselective alpha-alkylation of a glycinate imine. These esters are 10 orders of magnitude more acidic than ethyl acetate and can therefore be alkylated in the presence of protic solvents. In this instance, the alkylation was conducted in a suspension of finely milled sodium hydroxide in toluene with only 3% of an enantiomerically pure quinine-derived phase transfer catalyst. The particle size of sodium hydroxide was critical for the success of this reaction. Despite the absence of covalent bonds between the reacting partners and the catalyst, an enantiomeric excess of 77% was attained. A final chromatographic purification gave the target product in 55% yield and 99% enantiomeric excess. Recently, a number of mostly iridium-based catalysts have been developed which enable the reversible dehydrogenation of primary alcohols and amines. Thus, such catalysts can be used to bring about the formation of an aldehyde from an alcohol, its condensation with some carbon nucleophile, and the hydrogenation of the intermediate olefin. In this example, a more affordable cobalt complex was found to catalyze such a reaction sequence. This is a typical example of the formation of a lithium ester enolate followed by hydroxyalkylation with an aldehyde, acetaldehyde in this case. If one considers the pKa values of both starting materials, this is actually an amazing reaction. Acetaldehyde is 10 orders of magnitude more acidic than the starting ester and could have just protonated the ester enolate. Acetaldehyde is, however, only sparsely enolized, and the deprotonation of non-enolized aldehydes and ketones is about 1 million times slower than the deprotonation of, for instance, alcohols or water. In THF at low temperature, the nucleophilic addition of the ester enolate to the aldehyde is sufficiently fast to outcompete the protonation of the enolate by the aldehyde, despite the huge differences of pKa values. So, what are the potential pitfalls? Esters of acidic alcohols, such as phenyl or methyl esters, can cause problems for several reasons. First, the corresponding enolates readily undergo Claisen condensation and alkoxide elimination. Then, if hydroxyalkylations of such enolates are attempted, the initially formed beta-alkoxide can undergo ring closure and yield beta-lactones, as shown here. Such reactions can be prevented by using less sensitive esters, for instance isopropyl or terz-butyl esters. Besides the already mentioned Claisen condensation and ketene formation, further potential side reactions include multiple alkylations and cyclopropanation during palladium-catalyzed allylations. On this and the next two slides, you'll find some additional recent examples to help you find suitable conditions for your ester. By SN2 refers to alkylations with alkyl halides, sulfonates or epoxides. And the hydroxy esters refers to alkylations of carboxylic esters that contain an unprotected hydroxyl group. The references on this slide report alkylations of esters with aldehydes, ketones or imines as electrophiles. On this slide you'll find some examples of alkylations with alkenes, alkynes and aliphatic alcohols. I've also added some recent examples of the alkylation of acylated chiral auxiliaries, but many more have been published. Because these reactions have been so thoroughly investigated, they offer a quick and predictable way to prepare enantiomerically enriched carboxylic acid derivatives. My next presentation is about the alkylation of enamines. These intermediates had their heyday in Gilbert Stork's time in the 1950s and 60s, but there have been some interesting developments in recent years.